Hi, in this video I'll talk about how to solve structural problems in general and focusing on bridge engineering in particular. Students will find it interesting and significant as it contains a variety of engineering subjects such as structural and material mechanics, topics in strength of material, topics in bridge engineering, topics in structural dynamics and earthquake engineering, damage and fracture mechanics, and other advanced topics such as structural health monitoring and retrofit of bridges. The problem that I am focusing on is reinforced concrete box girder decks on single and multiple piers, and it's more architecturally suitable to have decks on single piers, and that's what makes the problem more difficult. There are different levels of vulnerability to damage, mode of failure, confinement and ductility, loading types and loading intensity. For the mode of failure in single columns, there is flexural and shear modes of failure. The flexural one is at transverse motion, and the shear mode of failure is at the longitudinal motion. And this is how it looks like when there is damage in the flexural mode. Another level of vulnerability is confinement and ductility. As we know, concrete is a quasi-brittle material, and it gets strengthened the more confinement it has. And that's why it will be having more deviatoric stresses, resisting more deviatoric stresses. In general, ductility of the reinforced concrete section is totally dependent on the reinforcement. And when there is no confinement or sufficient confinement, concrete will start to fracture even before the steel bars becomes plastically ductile. So when there is low axial load due to low weight of the viaduct, there will be low confinement, and then will be less integrity and less ductility, and then more vulnerable to damage. Another level of vulnerability is the peak response to strong motion, and this is what is known as the peak ground acceleration, or PGA. In this example, for example, this is 1989 Loma Prieta earthquake. The PGA was not high enough, it was not even high, but the problem was with the type of soil. It was a soft soil, even though the site was 100 kilometers away from the epicenter of the seismic fault. Another level of vulnerability is the long duration pulse. It's not always the PGA, it's many times the PGV, which is the peak ground velocity. It happens when long duration impulses and low frequency, and that's even that cause further damage. Now, when several levels of vulnerability combine together at one structure, it is very important for the engineers to think of other alternatives in terms of structural systems and in terms of methods of analysis. And this is what I consider as an engineering key concept. So, in terms of alternatives in structural systems, an engineer can think about other alternatives in the connection between the superstructure and the substructure, such as seismic isolation bearings, carbon fiber reinforced polymers, buckling resistant braces, and even seismic energy dissipation braces. Other alternatives in the methods of analysis, it includes the damage assessment and fracture analysis. This is very important to verify the seismic design criterion when we have the typical design of demand capacity principle the fracture analysis will verify our results. And it also will verify the workability of the damage control devices. Now, because of this, another branch of engineering has emerged. It's the performance-based seismic engineering, which is PBSE. The definition of performance-based seismic energy is that the structure's performance to dissipate the seismic energy within acceptable limited levels of damage. Now, there are topics in PBSE which is an engineer should have some knowledge about it: the damage indices, the shaking table experiments, and the numerical modeling. In respect to damage indices, actually a damage index is a qualitative manner based on previous experimental and site observations. So there are previous observations that we have before, and we can assess the damage in according to that. Or it can be based on the load deflection relation in a monotonic loading, which is known as the pushover test. And we have different damage degrees. In concern to the shaking table tests, the shaking table tests are experimental work that verify the validity and reliability of the proposed engineering problem. Now, when we go to numerical models, we have to have we have a lot of alternatives. But for an engineer, it's important to think about the one that is more suitable to his problem. Now, for example, this is a continuum damage model, CDM, which is actually based on determining the changes in the constitutive laws governing the cracking material without the need for refinement of the mesh. So without refining the mesh, we can control the constitutive laws that are governing the cracking inside the material, the continuum. For example, it's how to update the material matrix after damage, which is D star, and it is related to how to update the modulus of elasticity and how to update the geometry or the geometric section, which is dependent on the initial area and the area after damage. In another numerical models, there are ones that are based on hysteresis models. Now, it's a hysteresis model that is built within the code itself, and we can choose the ones that are more suitable to our problem, such as Clough hysteresis model, hysteretic model, slip model, Takeda model, and others. Now, even with the elements, the engineer can choose the code that have the most suitable element to it. There is, for example, for this particular problem, the fiber elements I found are very suitable in that matter. So, because it's a midway between the 3D tetrahedral elements and the 2D beam column. So, beam column elements. So, fiber element and also the lattice elements are very important as elements in this kind of problem in numerical models. Thank you. I hope you enjoyed it. Thank you very much.